Dear students, in this class, we are going to see the concept of thermal runaway and thermal stability. Everybody knows maximum average power will be dissipated across the collector junction in a transistor. The average power will be in the range of milliwatts to 150 watts, and it also depends on the type of the material you have used for the construction and the transistor properties. So now let me say clearly the concept of the thermal runaway that is existing in the transistors. So you take the transistor here having three terminals, emitter, base and collector, and having two junctions, emitter junction as well as the collector junction. Emitter junction is forward biased and collector junction is reverse biased. And if the collector current increases, maximum power will be dissipated across this collector junction, because you know the mathematical expression that is existing for this collector current, IC is equal to beta times IB plus beta plus 1 times ICO, that is nothing but the reverse saturation current. So this reverse saturation current ICO, generally it doubles for every 10 degrees rise in temperature. That means it is a temperature phenomena. It is a current which is existing in the reverse biased diode. The reverse biased diode is nothing but the output junction of the transistor. So whenever the temperature increases, your ICBO increases from this equation, ICBO increases. ICBO increases means ICEO increases, because this is ICEO. ICEO means reverse saturation current in common emitter configuration. It is the reverse saturation current in common base configuration. So if ICBO increases, ICEO increases, in turn IC also increases. If IC increases, once again the temperature at the collector junction increases. And if temperature increases, once again this process continues. So it is a cumulative process. It is going on continuing like this. After some time, whenever the temperature crosses the maximum temperature handling capability of this transistor, and it will be damaged. So cumulatively it is going on like this, and after some time the transistor is going to be damaged. That is called as thermal runaway. Thermal runaway is nothing but a cumulative process where the self-destruction of the transistor takes place. The transistor is going to be damaged because of this temperature rise in a cumulative process. So to avoid this thermal runaway, we have to see that whatever the heat that is evolved at the collector junction should be dissipated to the surroundings. So here the heat is actually liberated. Here the heat is generated at the collector junction, and it should be guided toward this space that is nothing but the surroundings. So in order to guide this power, in order to guide this heat to the surroundings, we require some mechanism. That mechanism is nothing but your heat sink. So you have to use the heat sink material to enhance the power handling capability of this transistor. So what is the heat sink? Heat sink is nothing but a metallic sheet. It is a metallic sheet attached to your transistor. So let me show it. It is nothing but a transistor. This is a power transistor. 2N3055 is a power transistor. This power transistor is having a metallic base. And whenever you are using in your power amplifiers, maximum heat will be generated. And if you are not taking any type of action to control this, the transistor is going to be damaged. Then what we do? We are going to take a metal base. This is nothing but the metal base here. This is the metal base, which is acting like a sink. And the sink will be attached to this transistor. And suppose if the heat is more, if you want to just totally remove this heat immediately, then the size of the heat sink may not be sufficient. Then the people are going for the big heat sink like this. So you can see it very clearly. This is the transistor. This is the power transistor. And whatever the material you are seeing in the black color, it is nothing but the heat sink. What is the function of this heat sink? It is immediately guiding the heat to the surroundings. That means it is removing the heat at the collector junction immediately. So it is actually totally transferring this heat to the surroundings, and that mechanism is nothing but the heat sink mechanism. That means air will flow very freely if you are having this type of structure for the heat sinks. Then immediately the transistor will be in the cool condition. So this type of heat sinks you can see it for our amplifiers, power amplifiers. Suppose if you want to address in a public, then you are going to use so many stages of amplifiers. At that time, maximum power will be generated at the collector. So immediately you have to remove this heat by adding a heat sink here. So heat sink you can see it practically. For example, if you take me, if I am getting a fever, generally it can be controlled with the tablets or something. Suppose if the fever is crossing 104, then the people will be fearing about it. So what we do? The rate of heat generation is more in the body. So immediately you have to send it to surroundings. Then what we do? We have to provide the heat sink for this. What type of heat sink we are providing? We are taking a wet cloth and we are putting like this. Or otherwise sometimes the doctor can suggest you to put the ice also, because it is the mechanism of removing the heat from the body immediately. If you are not taking care of this heat, whatever that is generating inside the body, then the person going to be damaged. Exactly here also, if you are not in a position to remove the heat immediately, the transistor is going to be damaged. That is only because of this thermal runaway. If the IC increases, temperature increases, again IC increases, temperature increases. Of course, we have taken so many measures while you are designing your biasing techniques. We have provided with the compensation techniques, but whenever you are going for some applications, those techniques also may not help you. So whenever the power is more at the collector junction, your duty is to see that the entire power should be dissipated to the surroundings immediately by providing the heat sinks. So if you are taking some regulators, some IC regulators, if you see it like this is a IC regulator. Here also you are just providing one aluminum sheet here. This can be acting like a heat sink. If the heat sink size is not sufficient, then you have to go for the big heat sinks like this. These are heat sinks. In some cases, the heat sink size will be very, very high. So it depends upon the power dissipation. It depends upon the power generation. So mathematically, I can say, if you want to protect your device, that is a transistor, whatever the heat that is liberated here, whatever the heat that is generated here, that heat has to go to the surroundings immediately. So dissipation of the power should be more compared to the generation. Mathematically, I can say here, let us say that Tj is nothing but the junction temperature. Tj is equal to junction temperature, and Ta is nothing but an ambient temperature. Ambient temperature means temperature of the surroundings. It is ambient temperature. Now, whatever the power that is actually dissipating from this collector junction, that is, let me say, PD, power dissipation is directly proportional to the steady state rise in temperature. What do you mean by steady state rise in temperature? Actually, the junction temperature is Tj. Ta means ambient temperature. What is the net temperature? Tj minus Ta. It is steady state rise in temperature is directly proportional to the power dissipated from the collector junction. So you can say that PD is equal to some proportionality constant theta into Tj minus Ta. So this is theta. This theta is called as thermal resistance. Thermal resistance. So what may be the unit of this thermal resistance? Thermal resistance theta is equal to PD by some temperature delta T. That means watts per degree centigrade. So the unit of theta, unit is watts per degree centigrade. This is the unit of the thermal resistance. So whatever the resistance that is offered for the thermal temperature is nothing but thermal resistance. In our electrical circuits, the resistance offered for the current flow is nothing but your resistance, electrical resistance. But here it is actually opposing the temperature flow. It is called as a thermal resistance. So PD is equal to theta into something like Tc minus Ta. This is the basic equation for this. This is the basic equation. Now, if you are taking this one, in order to protect the transistor from damaging, what we have to say is, whatever the power that is actually generated at the collector junction, the rate of power that is generating at the collector junction should be less than the dissipated power. So you can say that at the collector junction, let me say, dou Pc by dou Tc must be less than or equal to dou Pd by dou Tc. That means at the junction, you have to satisfy this condition. This is nothing but the power that is generated in the collector. The rate of power that is generated in the collector must be less than or equal to the rate of power dissipation at this collector junction. So, if the generation is less than the dissipation, the transistor always will be in the cool condition. Suppose, for example, if the generation is more and the dissipation is less, then it will be always in the hot condition and it is going to be damaged. So, this way you have to understand, to avoid this thermal runaway, you have to use this condition. Why this thermal runaway comes into the picture? Because of the cumulative process. If temperature increases, IC increases. If IC increases, temperature increases. If you are not taking care of this, then it is a cumulative process, and after some time, because of the temperature, the transistor is going to be damaged. That self-destruction of the transistor is called as thermal runaway. That thermal runaway can be avoided if you are using this condition. Now, this is the condition you have to achieve for protecting this transistor. Exactly. One more thing is, you have to protect this transistor by using some mechanism that is nothing but the heat sink, that what I have explained. So, heat sink is nothing but a metallic sheet. So, if you take this heat sink is nothing but a metallic sheet. It is the metallic sheet, just now I have shown you. And what are the things that are required for better usage of this heat sink? So, the very first one is, for maximum efficiency, it should be in good thermal contact with the transistor. So, this is the transistor, this is the transistor, and this is the transistor, and it is the case we are using. It should have some perfect thermal contact, because if it is having the perfect thermal contact, the heat that is liberated at the collector, that will be actually transferred because of the conduction. So, whatever the heat that is developed at this collector, it should be transferred to this heat sink through conduction. For better conduction, you have to fit it perfectly. It should have a perfect contact. Then only the maximum heat will be given to this heat sink. So, once the heat is given to this heat sink, and it will be going to the surroundings either by convection or conduction process. What is the second one? It should have a large surface area. If the heat sink is having the large surface area, immediately it can send the heat to the surroundings. The third one is, it should be painted black. Black color is having the advantage of absorbing the heat immediately. In winter season, the people are going for the black cloths. Why? It has to absorb the heat. And this heat sink, if it is in black color, it is going to absorb this entire heat very fast from the transistor. And the fourth one is, it should have airflow to pass through it. So, as this construction is having different types of laminated cores like this, whenever you are supplying the air to this, maximum air will be supplied to the transistor base. Then it will be cool. So, that's why one way, hardware point of view, I am telling you, to avoid this thermal runaway, you have to provide the heat sink. There are different types of heat sink you can use, and the design will be actually changing depending upon the transistor ratings and the power dissipation capabilities. Okay. Now, we are going to see the concept of thermal resistance, and we are going to find the expression required to avoid this thermal runaway. Just now I told you, thermal runaway is unwanted concept in the transistors. So, if you take this transistor, it is the collector junction. Let us say that Tj is nothing but the junction temperature, Ta is an ambient temperature. So, if you take this difference of these two, that is called steady state temperature, Tj minus Ta is directly proportional to the power that is dissipated across the collector junction. If you remove this proportionality, you can write here Tj minus Ta is equal to theta into Pd. This theta is nothing but your thermal resistance. So, from this I can write down theta, thermal resistance is equal to Tj minus Ta divided by Pd. So, what is the unit of this thermal resistance? Thermal resistance unit is temperature by power. Temperature means degree centigrade divided by watts. This is the unit of your thermal resistance. So, thermal resistance means it is the resistance which is actually opposing the heat flow from one place to the other place. Exactly like our electrical resistance which opposes the current flow there. And here this thermal resistance means it is actually opposing the heat flow from one place to the other place. So, once you know this thermal resistance, differentiating this equation on both sides with respect to Tj, then you can say that with respect to Tj it becomes 1 is equal to theta into dou Pd divided by dou Tj. Therefore, dou Pd by dou Tj is equal to 1 by theta, thermal resistance. Let this equation is 1. So, change of power dissipation with junction temperature is equal to 1 by theta. Theta is a thermal resistance. I already told you, in order to avoid this thermal runaway, whatever the heat that is dissipated from this junction should be more compared to the heat generation. But what is the heat generation here? Dou Pc by dou Tj, dou Pc by dou Tj should be less than or equal to the dissipated power. The dissipated power is Pd. So, it is dou Pd by dou Tj. This is the condition required to avoid the thermal runaway. Let it be the second equation. So, the second equation is telling dou Pc by dou Tj should be less than or equal to dou Pd by dou Tj. For example, if you are taking the collector junction here and at the junction, let us say that 10 degrees centigrade for watt is actually generating and 8 degrees centigrade for watt is actually dissipation to the surroundings. So, generation is more, dissipation is very less. It is a dangerous condition. The transistor is going to be damaged. Suppose the 10 degrees centigrade for watt is actually generating and 15 degrees centigrade for watt is actually going to the surroundings, then it is the safest condition. The meaning is very simple. The rate of power dissipation should be more compared to the rate of power generation at the collector. So, that thing actually that can be explained by this equation. Okay. From the equation 1 and 2, you can write dou Pc by dou Tj should be less than or equal to dou Pd by dou Tj. What is dou Pd by dou Tj from equation 1? 1 by theta. So, this is the condition required for thermal stability. So, this is telling about thermal stability. So, once you know this, then you can write down the condition required to avoid the thermal runaway also. So, I can write down this dou Pc by dou Tc as dou Pc by dou Tc is equal to dou Pc by dou Ic multiplied by dou Ic divided by dou Ic naught multiplied by dou Ic naught divided by dou Tj. This is the equation. So, finally, this and this will be cancelled, this and this will be cancelled, dou Pc by dou Tj. Now, just observe carefully, dou Pc by dou Tj is equal to dou Pc by dou Ic, dou Pc by dou Ic multiplied by dou Ic by dou Ic naught. What it is? Variation of Ic with reverse saturation current is nothing but a stability factor. Yes, S into, it is rate of change of reverse saturation current with temperature. You know very well, in germanium and silicon transistors, on average, there will be a variation of 7% per degree centigrade. That's why you can write down here, it is 0.07 IC naught. This is also a constant. So from this, I would like to calculate what is dou PC by dou IC. So what is PC? PC means the power dissipated at the collector junction. So power PC is equal to IC into the voltage across the collector to base junction, VCB. So VCB means this is the collector to base. This is approximately equal to VCE because this VB is neglected. It is a small drop. That's why it is approximately equal to VCE into IC. So what is VCE? VCE means the output voltage for the circuit. This output voltage for the circuit is VCC minus ICRC minus ICRE because I is approximately equal to IC. So you can write here PC is equal to IC into, in the place of VC you can write down VCC minus IC into RC plus RE. This is the expression you can write from your circuit. Now just calculate this. PC is equal to VCC into IC minus IC square into RC plus RE. This is the calculation of the power for the collector junction. So let it be the equation. This is 3. Okay, equation 3. Now we are going to calculate dou PC by dou IC by taking this equation. So PC is equal to VCC into IC minus IC square into RC plus RE. Now differentiate with respect to the collector current. Dou PC by dou IC is equal to, with respect to IC it is 1, it is VCC minus IC square means 2 times IC into RC plus RE. RC plus RE. Now this thing you have to substitute in the main equation, that is dou PC by dou TC is equal to dou PC by dou IC into the stability factor into 0.07 IC naught. So in the place of this dou PC by dou IC, just substitute this substitute here. Therefore, dou PC by dou TC is equal to VCC minus 2IC into RC plus RE multiplied with the stability factor multiplied with 0.07 IC naught. IC naught. So this should be dou PC by dou TC should be less than or equal to 1 by theta, which is nothing but the thermal resistance. It is the condition required for getting the thermal stability. So it should be less than or equal to 1 by theta, thermal resistance. Here the logic is, remember my dear friends, see this is VCC minus 2IC times RC plus RE, it is called dou PC by dou IC on the stability factor, and this is with respect to reverse saturation current, and this is thermal resistance. Remember here, this thermal resistance is always positive and the stability factor is always positive. It is the change is positive. Here 0.07 IC naught is also positive. This is also positive. In order to satisfy this condition, as the theta is thermal resistance is having some value, in order to satisfy this condition, 100% whatever the things you are having this is dou PC by dou IC should be negative. It should be negative. That means it always should be less than or equal to 0. Therefore, I can write here from this conclusion, VCC minus 2 times IC into RC plus RE should be less than or equal to 0. This is the condition required. Why? Because this is very, very important to satisfy this condition. Because this condition is required to avoid this thermal runaway. That is called for getting the thermal stability. So that's the reason it should be always less than or equal to 0. Now add VCC on both sides. So it becomes 2 VCC minus 2 IC into RC plus RE less than or equal to VCC. Therefore, it can be written as VCC minus 2 minus IC into RC plus RE is less than or equal to VCC by 2. This 2 is from this term and as well as this term. Therefore, I can say VCC minus IC into RC plus RE, which is actually the output voltage VCE. This entire thing you can replace with VCE. Therefore, I can write down VCE should be less than or equal to VCC by 2. So, always remember friends, whatever the output voltage that is existing here, it should be always less than or equal to VCC by 2. What is this VCC? Whatever the VCC you are giving for the biasing purpose. So, just listen here, if you are taking this common emitter configuration here, and this is the VCC, and the output voltage is VCE. In order to avoid this thermal runaway and for getting the thermal stability, the condition required here is your VCE should be less than or equal to VCC by 2. That means under any circumstances, if the output voltage is less than or equal to half of the applied voltage, then we are going to get the thermal stability. This is the condition required to avoid your thermal runaway or for getting the thermal stability. I hope you understood the concept of thermal runaway and thermal stability. Thank you.